Traditional game theory treats the rules of the environment as fixed. The analyst observes an existing system, assumes the participants are rational actors, and calculates the resulting strategies and equilibria. Advanced microeconomic theory, detailed in the foundational Mascowell, Winston, and Green text, approaches these interactions from the opposite direction. This is mechanism design, reverse game theory. The desired social outcome is the starting point, while the institutional rules must be engineered from scratch to achieve it. Rather than predicting human behavior within an existing environment, the designer constructs an environment that guarantees a specific behavioral response. Mechanism design functions as a problem of constrained optimization. The designer maximizes a social objective by building a framework that accounts for the strategic realities of human self-interest. To achieve perfect outcomes requires having perfect information. However, the data the designer needs most is often privately held by the participants themselves. In this framework, private knowledge is defined as an agent's type, denoted as theta I. This represents their hidden valuations, costs, or risk profiles. Agents have a natural incentive to misreport these types. A farmer enrolling in a conservation program may exaggerate their opportunity costs to extract a larger payout from the regulator. This creates adverse selection. This informational friction occurs when high-cost or high-risk agents use their hidden types to masquerade as low-risk agents, exploiting the system for private gain. Without a system mathematically hardened against hidden information, self-interested agents will prevent the attainment of the designer's optimal social outcome. The designer begins with the social choice rule, or SCR. The SCR is a target mapping, f of theta in x, that dictates the specific efficient allocation the designer wants to implement based on the true state. The mechanism is the institutional machine built to achieve that SCR. The mechanism's first component is the message space, MI, dictating what agents can communicate. The outcome function, G, translates those messages into the final allocation. Combined with an equilibrium concept, this generates an outcome based on true types and strategies. Searching every possible message space and outcome function is practically unsolvable due to infinite dimensions. The revelation principle simplifies mechanism design, formally reducing the designer's search space. The theorem proves that if an outcome is implemented by a complex mechanism, it can be implemented by a direct revelation mechanism. Here, the only message space is reporting true types. The rules are set so truthful reporting is the equilibrium. This doesn't guarantee every rule is implementable. It simply restricts the search to truthful mechanisms. The designer stops inventing complex rules. The problem becomes an optimization, where truth-telling is the best strategy. A direct revelation mechanism is valid only if it respects two mathematical boundaries. The first is individual rationality, or IR, also known as the participation constraint. The second is incentive to viability, or IC. This rule ensures reporting the truth strictly maximizes utility. Since participation is typically voluntary, the mechanism must guarantee an outcome that meets or exceeds the agent's baseline outside option. Dominant strategy incentive compatibility, or DSIC, is the most robust form of this constraint. Truth-telling remains optimal regardless of what any other participant does. By contrast, Bayesian incentive compatibility, or BIC, is a more flexible constraint. It only requires that truth-telling is optimal on average, based on the agent's probabilistic beliefs about others. The designer simply chooses allocation and transfer rules subject to these boundaries, ensuring participation and truthful reporting. The Vickery-Clark-Groves, or VCG, mechanism is the canonical solution for achieving perfect efficiency while satisfying the strict DSIC constraint. VCG operates in quasi-linear environments, where an agent's utility equals their valuation of the outcome minus their monetary transfers. The Clark pivot rule sets transfers by comparing the value others receive without the agent to the value with them. This fee equals the exact utility drop the agent imposes. It's like picking a movie and paying a tax for your friend's lost happiness. This fuses private utility with social surplus. There is no longer a financial benefit to lying about your preferences. VCG achieves efficiency by making truth-telling a dominant strategy, forcing the individual to internalize the social cost of their desires. Despite its elegance, VCG has real-world limits. It ignores revenue generation, requires quasi-linearity, and frequently runs budget deficits. Designers usually face the canonical optimization problem, where they must maximize specific objectives, like a regulator's budget, rather than theoretical efficiency. A first-best scenario involves full information and frictionless redistribution. This is often unattainable. In the second-best reality of private information, a fundamental trade-off exists. The designer cannot extract all surplus while simultaneously inducing truthful reporting. The inescapable existence of hidden information forces the designer to accept these structural inefficiencies to maintain a functional mechanism. One unavoidable cost is information rents. High-type agents receive extra utility, so they don't mimic low-type agents. To reduce the cost of these rents, the designer must make the prospect of lying less attractive without increasing payments. This is achieved through allocative distortions, degrading the outcome for lower types. Software companies cripple basic versions by removing costless features. The basic tier is made so unappealing that power users are forced to reveal their high-value status by purchasing Pro. Similarly, conservation programs may exclude marginal, inexpensive land, specifically to prevent wealthy farmers from claiming those lower payment tiers. The presence of an intentionally crippled product or an inefficient policy is evidence of the mathematical price required to uncover a secret. Mechanism design begins with optimal targets, applies the revelation principle to simplify, and builds around human self-interest. These resulting distortions and rents map the boundaries of what institutions can achieve when human minds remain private. Stability is achieved not by demanding honesty, but by engineering an architecture where honesty is the most selfish choice possible.